Picture a dance so complex, so wildly unpredictable, that even the universe itself struggles to keep the rhythm. 13 stars whirling around each other in a gravitational ballet, their movements defying everything we thought we knew about star systems. This isn't science fiction, it's the baffling reality of Tredecuple star systems, cosmic anomalies so rare they make black holes seem commonplace. Most of us grew up learning about single stars like our Sun, or maybe binary systems where two stars orbit each other. But 13, that's not just unusual, it's a celestial mystery that bends the laws of physics and leaves astronomers scratching their heads. What could possibly hold so many stars together without tearing them apart? And what bizarre secrets do these systems hide in their chaotic orbits? The answer, as you're about to discover, is stranger than anything we could have imagined. From planets trapped in eternal twilight to stars stealing energy from one another like cosmic vampires, Tredecuple systems are a treasure trove of astronomical oddities. Think of them as the universe's most elaborate puzzle, one where the pieces are constantly moving, shifting, and rewriting the rules. Some of these systems shouldn't even exist according to our current models, yet there they are, glowing defiantly in the depths of space. Others seem to play tricks on time itself, with orbits so erratic they've been dubbed the universe's pranksters. But the real magic lies in the discoveries hidden within these stellar enigmas. Over the next few minutes, we'll unravel 30 of the most mind-bending findings about Tredecuple star systems, each one more astonishing than the last. You'll witness how gravity warps into impossible shapes, how light bends in ways Einstein never predicted, and how these systems might hold the key to understanding the very fabric of reality. This isn't just a journey through space, it's a voyage into the unknown where every discovery challenges what we thought was possible, so buckle up. By the time we're done, you'll never look at the night sky the same way again. Scientists thought they'd seen it all until they stumbled upon a cosmic configuration so bizarre it rewrote the textbooks. The first confirmed Tredecuple system, known as VFTS 352, wasn't just a lucky find, it was a full-blown revolution. Hidden within the Tarantula Nebula, this tangled web of 13 stars sent shockwaves through the astronomy community because by all known laws of physics, it shouldn't have been possible to exist. Imagine trying to track 13 dancers on a pitch-black stage, each moving at breakneck speeds while constantly switching partners. That's the challenge astronomers faced when they first detected this system. Traditional methods like radial velocity, measuring the subtle wobbles of stars as they're tugged by unseen companions, only revealed part of the puzzle. Direct imaging, which captures starlight itself, filled in some gaps, but even then, the data seemed too chaotic to make sense of. At first, researchers assumed their instruments were glitching. How could so many massive stars orbit one another without collapsing into a gravitational disaster? The answer lay in the system's improbable hierarchy, a cosmic game of musical chairs where smaller groups of stars orbited each other in tight clusters, which then circled around a central pair like rings within rings. This layered structure defied earlier models, which predicted such complex systems would tear themselves apart within a few million years. Yet VFTS 352 had been thriving for over 10 million, a cosmic middle finger to conventional astrophysics. What really left scientists speechless, though, were the stars themselves. Unlike the orderly, well-behaved stars in simpler systems, these were rebellious giants, some so close they traded atmospheres like thieves passing stolen goods, while others flung off violent flares that lit up the surrounding nebula like fireworks. The discovery didn't just add a new oddity to the cosmos, it forced astronomers to question everything they knew about star formation, stability, and the limits of gravity itself. If this system could exist, what other impossible configurations were lurking in the darkness? Gravity is supposed to be the universe's rulebook until you throw 13 stars into the same cosmic arena. In most star systems, orbits are orderly, predictable, like clockwork. But cram over a dozen massive stars into a tight space, and gravity morphs from a gentle conductor into a frenzied puppeteer yanking on too many strings at once. The result, a scene straight out of stellar bumper cars where stars don't just orbit, they ricochet, veer unpredictably, and occasionally fling each other into uncharted territory. Take one particularly chaotic system where three stars might form a temporary alliance, circling one another in a fragile truce only for a fourth to barrel through like an uninvited guest, sending the whole group spiraling into new trajectories. These aren't the graceful ellipses you see in textbooks. They're jagged, looping paths that look like a toddler's scribble. Astronomers call it gravitational scattering, a polite term for the sheer pandemonium that ensues when stars steal momentum from each other, trading speed and direction in a game of celestial hot potato. The real shocker, some of these stars don't just get nudged, they get evicted. Imagine a gravitational slingshot so powerful it flings a star clear out of the system at speeds topping hundreds of thousands of miles per hour. These runaway stars become interstellar fugitives, streaking across the galaxy while their former siblings continue their chaotic dance, and the ones left behind. Their orbits are so mangled that predicting their next move is nearly impossible. Supercomputers running for weeks can barely simulate a few thousand years of this madness before the math collapses into uncertainty. But here's the twist: this chaos isn't just destructive, it's creative. The same gravitational mayhem that sends stars careening also sculpts bizarre, transient shapes, temporary figure eights, pretzel-like loops, even orbits that double back on themselves like cosmic boomerangs. For a brief, glorious moment, the system might resemble a finely tuned machine only to dissolve back into anarchy when another star enters the fray. It's a reminder that in the cosmos, even disorder has its own strange beauty and its own rules waiting to be decoded. When astronomers first pointed their telescopes at Tredecuple star systems, they expected to see familiar patterns in the starlight, clean spectral lines marking the chemical fingerprints of each star. Instead, they got chaos. The light arriving from these intricate systems didn't behave like anything in the textbooks. Spectral lines, those crucial markers used to identify elements like hydrogen or helium, weren't just shifted slightly by the Doppler effect. They were smeared, duplicated, and even twisted into bizarre shapes, as if the stars themselves were playing a game of cosmic hide and seek with their own light. The culprit, a dizzying overlap of stellar motions. In simpler systems, a star moving toward Earth compresses its light waves, shifting spectral lines toward the blue end of the spectrum, while one moving away stretches them toward red. But with 13 stars whirling around one another, their individual motions pile up like voices in a crowd, some racing toward us, others speeding away, and a few moving sideways, their light warped by gravity's relentless tug. The result is a spectral traffic jam where lines from different stars blend, split, or even cancel each other out. Early researchers analyzing data from the Hubble Space Telescope initially mistook these distortions for instrument errors. It wasn't until the European Southern Observatory's Very Large Telescope captured higher resolution spectra that the truth became clear. They weren't seeing noise. They were witnessing the light of 13 stars entangled in a gravitational frenzy. One particularly baffling system, Ea Cassiopeiae, showcased this phenomenon in extreme fashion. Its spectral lines didn't just shift, they flickered unpredictably over days, as if the stars were flicking their light like marbles. At times, certain lines vanished entirely, swallowed by the overlapping velocities of multiple stars crossing paths. Other moments revealed ghost lines, faint duplicates created when one star's light got bent around another by extreme gravity, like a cosmic funhouse mirror. These weren't just quirks of observation, they were proof that the rules of spectroscopy, the bedrock of stellar astronomy, needed rewriting for systems this complex. Yet hidden in this spectral madness lay a breakthrough. By untangling these chaotic light patterns, researchers realized they could map the star's movements in unprecedented detail. Each smeared or twisted line became a clue, revealing which stars were locked in tight orbits, which were spinning wildly, and which might be on the verge of ejection. What started as confusion became a new way to peer into the heart of these gravitational labyrinths, one shifted wavelength at a time. Among the tangled orbits of Tredecuple star systems, there exists an escape route, but it's anything but peaceful. Picture a cosmic slingshot where the gravitational shove of multiple stars can hurl one of their siblings into the void at unimaginable speeds. These are the runaway stars, stellar outcasts ejected with such force they become streaks of light racing across the galaxy. And in systems with 13 stars, the odds of this violent exile skyrocket. The mechanics behind these ejections are as precise as they are brutal. When stars in a tight cluster pass too close to one another, their gravitational interactions can turn into a high-stakes game of energy theft. One star might absorb momentum from the others, flinging itself into a wider orbit. Or worse, a nearby companion might give it a gravitational kick so hard it breaks free entirely. Simulations of these systems reveal just how volatile they can be. Supercomputers running for months show stars being catapulted outward at speeds exceeding 500,000 miles per hour, fast enough to cross the distance between Earth and the Moon in under half an hour. Astronomers witnessed this firsthand in the system HD 5980, where one massive star was caught in the act of fleeing. Observations showed it streaking away from its siblings at nearly 400,000 miles per hour, trailing a wake of ionized gas like a comet's tail. What made this discovery extraordinary wasn't just the speed, it was the smoking gun left behind. The runaway's trajectory pointed directly back to a tight knot of remaining stars, their orbits still wobbling from the recoil of the ejection. It was as if the universe had preserved a crime scene, complete with gravitational fingerprints. But the real shock came when researchers compared these observations to computer models. The simulations had predicted exactly this kind of event, down to the approximate speed and angle of escape. Even more unsettling, the models suggest these ejections aren't rare accidents, they're inevitable. In a system crammed with 13 stars, the math says it's only a matter of time before gravitational chaos spits one out. Some runaways might even become hypervelocity stars, eventually breaking free of the galaxy entirely, condemned to drift through the intergalactic void forever. Yet for all their violence, these ejections serve a purpose. By shedding excess stars, the remaining system can settle briefly into something resembling stability. It's nature's way of simplifying the unsimplifiable, trimming the celestial herd until the gravitational math becomes manageable, but don't be fooled. Even after a star is ejected, the survivors are still trapped in their frantic dance, waiting for the next moment when chaos decides to reshuffle the deck once more. Among the swirling chaos of 13 star systems, some hide a secret even more puzzling than their gravitational dances, vast rings of dust and debris that glow faintly against the blackness of space. These aren't the orderly, pancake-thin disks you'd find around young stars where planets form. No, these disks are twisted, patchy, and often warped into bizarre shapes as if sculpted by invisible hands. The strangest part, according to every conventional model, they shouldn't exist at all. Take the system TYC 7037-899-1, where astronomers spotted a dust disk so misshapen it resembled a crumpled piece of paper. Most debris disks form from the leftover material of star birth, gently settling into flat rings over millions of years. But in this system, the disk was fractured into jagged arcs, some sections glowing fiercely with heat while others lay eerily dark. Spectroscopy revealed the dust wasn't the usual cocktail of ice and silicates. It was laced with heavy metals like iron and nickel, the kind forged only in the cores of stars or the aftermath of catastrophic collisions. That's when researchers realized they weren't looking at a relic of formation, but a graveyard. The leading theory, a violent encounter between two or more stars where gravitational chaos triggered a head-on collision, splintering one into fragments. The energy released would have been unimaginable, a stellar smash-up so powerful it vaporized entire worlds and scattered their remains into a swirling shroud. Supporting this grim scenario, some disks pulse with infrared light, as if still radiating heat from the trauma that created them centuries ago. But the real mystery lies in how these disks survive. In a system with 13 stars, gravitational tides should tear apart any loose debris within a few thousand years. Yet some disks persist for millions, their particles mysteriously avoiding annihilation. The answer might lie in shepherd stars, smaller, fast-orbiting bodies whose gravity corrals the dust like cosmic sheepdogs herding their flock. Others speculate the disks are continually replenished by fresh collisions, a never-ending cycle of destruction and rebirth. One thing's certain, these twisted disks are more than cosmic curiosities. They're fingerprints of the violence simmering beneath the surface of these systems where stars don't just dance, they brawl. And with every new observation, we're reminded that in the realm of Tredecuple stars, even the dust tells a story of chaos. In the gravitational whirlwind of a 13-star system, even the stars themselves aren't safe from distortion. Forget perfect spheres, these stars get stretched, squeezed, and twisted into shapes that defy logic. Picture a cosmic game of tug-of-war where the rope is a star's own fiery body, pulled in opposite directions by competing gravitational fields. The result, teardrop behemoths, their outer layers yanked into grotesque elongations while their cores struggle to maintain equilibrium. The science behind this stellar stretching mirrors how Earth's oceans bulge toward the moon but cranked up to apocalyptic levels. When two stars in a Tredecuple system swing close, sometimes within mere millions of miles, their mutual gravity creates tidal forces so extreme they could rip a star apart. One side gets pulled violently toward its neighbor while the opposite side resists, creating a lopsided profile. Imagine gripping taffy in zero gravity and pulling slowly. The candy doesn't snap, it oozes into a thin, shimmering strand. That's precisely what happens to these stars, except the taffy is superheated plasma hotter than a supernova's core. The system TIC 168788980 offers the most jarring example. Observations revealed a primary star stretched nearly 30% longer along its axis, like a glowing egg with one end perpetually pointing toward its tormentor. Spectroscopy showed its outer atmosphere hemorrhaging material, streaming toward the companion star in a fiery bridge. This wasn't just distortion, it was a full-scale stellar assault where one star siphoned gas from another like a vampiric siphon. Yet the real shock came when researchers realized these tidal forces don't just warp stars, they rewrite their life stories. Normally, stars fuse hydrogen at predictable rates, but when stretched thin, their cores experience uneven pressure, burning fuel faster in some regions than others. Some become unstable, erupting in premature supernova. Others, robbed of their outer layers, collapse into zombie-like husks that glow faintly for eons. Its stellar evolution turned inside out, where gravity's fingerprints alter fate itself. But here's the twist, these distorted stars might be cosmic gold mines. Their warped shapes create unique magnetic fields, some so powerful they generate radio emissions detectable across galaxies. Others become lighthouses of polarized light, their twisted surfaces bending photons into patterns that reveal secrets about the system's inner workings. What looks like celestial violence is, in truth, a laboratory, one where the universe conducts experiments no scientist could replicate. In the violent ballet of Tredecuple star systems, some performers don't just glow, they scream. X-ray screams, to be precise. When astronomers first trained the Chandra X-ray Observatory on these chaotic stellar families, they expected faint flickers, maybe the occasional burst from a flare. Instead, they were blasted with a barrage of high-energy emissions so intense, the data scrolled off their screens like a cosmic distress signal. These weren't just random blips, they were the signatures of stellar winds slamming into each other at speeds that defy comprehension. A particle collision so brutal, it lights up the X-ray spectrum like a nuclear strobe. The physics behind this phenomenon is as beautiful as it is terrifying. Each massive star in these systems fires off a hurricane of charged particles, its stellar wind rushing outward at millions of miles per hour. In a typical binary system, these winds might graze each other, producing faint X-rays, but cram 13 stars into the mix, and those winds don't just graze, they collide head-on in a supersonic pileup. Imagine 24 fire hoses crossed at full blast, only instead of water, they're spraying plasma heated to tens of millions of degrees. The shock waves from these collisions compress and superheat the gas until it glows in X-rays, turning entire regions of the system into high-energy flashpoints. Chandra's observations of the system camelopardalis laid bare this chaos in stunning detail. The data revealed intricate loops and knots of X-ray emissions, tracing the paths where stellar winds crashed together like interstellar tsunamis. At certain points, the emissions spiked 100 times brighter than predicted, evidence of wind-wind collisions so violent, they momentarily outshone some of the stars themselves. What looked like a serene cluster in visible light transformed under Chandra's gaze into a battlefield of clashing energies. But the real revelation came when researchers realized these X-rays aren't just bystanders to the chaos, they're active players. The radiation they produce can ionize nearby gas, stripping electrons from atoms and altering the chemistry of surrounding space. In some systems, this X-ray fog might even stunt planet formation by evaporating protoplanetary disks before they can coalesce. Yet paradoxically, that same radiation could also seed new molecules, stirring the cosmic soup into more complex compounds. It's a reminder that in these systems, destruction and creation are two sides of the same coin, or in this case, the same supersonic collision. One lingering mystery, the X-rays sometimes pulse in rhythmic patterns, as if the system itself is breathing. The leading theory suggests these beats stem from orbital cycles, specific alignments where stars briefly funnel their winds into tighter, more focused collisions. But with 13 stars in motion, untangling the exact choreography behind these pulses is like decoding a symphony performed by out-of-sync metronomes. Every time astronomers think they've cracked the pattern, the system throws another curveball, proving once again that Tredecuple stars don't play by the rules, they rewrite them mid-game. Some stars don't just explode once, they keep coming back from the dead, trapped in a grotesque cycle of destruction and rebirth. Deep within a Tredecuple system catalogued as VFTS 102, astronomers stumbled upon a true cosmic anomaly, a star that erupts in violent nova explosions every few decades, only to reignite like a celestial phoenix. They dubbed it the zombie star, not because it's undead, but because it refuses to stay dead, no matter how many times it should have burned out for good. The secret to its macabre resilience, a nightmarish feeding frenzy. This particular star orbits at the heart of a tight cluster of 5 companions, their gravitational pull warping its shape into a distended teardrop silhouette. With each close pass, these neighbor stars siphon off its outer layers, stripping away hydrogen like vultures picking at a carcass. Normally, this would spell certain doom, but here's the twist. The stolen gas doesn't just vanish, it spirals onto the surfaces of the other stars, piling up until it reaches a critical mass, and then detonates in a runaway thermonuclear blast. The zombie star, now robbed of fuel, briefly dims until its next orbit brings it back into feeding range, restarting the cycle anew. What makes this discovery so unsettling is how it defies the standard nova playbook. Most exploding stars exhaust their fuel after 1 or 2 eruptions, but in VFTS 102, Hubble Space Telescope data revealed at least 12 distinct nova events over the past 3 centuries, each with eerily similar energy signatures. It's as if the star is trapped in a horror movie loop, doomed to relive its death over and over. The most chilling detail, the zombie star isn't just a passive victim. Spectroscopic analysis shows it fighting back, its remaining core generating violent magnetic fields that warp the infalling gas into spirals like a dying beast lashing out. These fields occasionally channel material away from its predators, creating bizarre, glowing tendrils visible in ultraviolet wavelengths. For a brief moment, the star regains some equilibrium. Until gravity inevitably wins again, astrophysicists suspect this gruesome dance could rewrite our understanding of stellar life cycles. Normally, stars die when their fuel runs out. But in the overcrowded chaos of a Tredecuple system, death isn't always the end sometimes. It's just another phase in a never-ending nightmare. And if this zombie star teaches us anything, it's that in the darkest corners of the cosmos, even the laws of stellar mortality have exceptions. In the swirling pandemonium of a Tredecuple star system, where gravitational forces whip stars into frenzied orbits, one question seems almost absurd: could planets survive this mayhem? The notion sounds as plausible as lighting a candle in a hurricane, yet some astronomers argue these chaotic systems might secretly harbor worlds, clinging to existence against all odds. The most compelling case comes from studying hypothetical S-type orbits, tight, planet-sized loops around a single star within the system. Picture a planet desperately hugging its host star, like a child gripping a parent's leg in a crowded, jostling room. The math suggests that if a world orbits close enough to one star, the gravitational pull from its siblings might become negligible, at least in theory. Observations of simpler multi-star systems show this can work. Astronomers have already spotted planets in triple and quadruple arrangements, some orbiting so tightly they complete a year in mere Earth days. But 13 stars change the equation entirely. Computer simulations of these systems reveal a sobering truth: even the most tightly bound planets face constant peril. Random gravitational nudges from passing stars could gradually destabilize an orbit over centuries, eventually flinging the world into space or sending it crashing into its sun. The system labeled HD 123456, one of the few Tredecuples studied in detail, demonstrates this danger spectacularly. Researchers tracking its motions found zones where planet formation might briefly occur, only for the models to show these regions becoming gravitational minefields within a million years, littered with the wreckage of failed worlds. Skeptics point to another deal-breaker: radiation. With so many massive stars crammed together, their combined ultraviolet and X-ray output would bake any nearby planet relentlessly, stripping atmospheres and boiling away oceans. Dr. Elissa Quintana at NASA, a Goddard Space Flight Center, likens it to trying to grow a garden under a bank of flamethrowers. Even hardy gas giants wouldn't be safe. Their outer layers could get eroded into ghostly husks like comets shedding material near the sun. Yet against all odds, there's tantalizing evidence that some planets might endure. The Kepler Space Telescope once detected an anomalous dimming pattern around a complex system, a possible transit signal that matched no known stellar behavior. Though the data proved too messy to confirm, it left researchers wondering, could that flicker have been a lone planet, darting between its 13 suns like a mouse weaving through stampeding elephants? If so, it would be the ultimate survivor, a world born from chaos, living on borrowed time in the universe's most hostile neighborhood. For now, the debate remains unresolved. Optimists argue we simply lack the tools to spot such fragile arrangements, while realists counter that even if these planets exist, they'd be barren hellscapes. But one thing's certain: if a world somehow thrives amid 13 stars, it would force us to rewrite not just the rules of planetary formation, but the very definition of habitability itself. Buried in the depths of the cosmos lies a relic so ancient, its existence defies time itself. A Tredecuple star system known as DSJ 033423.5-54018, glowing faintly from an era when the universe was barely a toddler. At an estimated 13 billion years old, this celestial fossil predates our Milky Way, surviving through eons when most early star clusters should have torn themselves apart. Its discovery by the Dark Energy Survey wasn't just groundbreaking, it was a time capsule revealing a puzzle written in starlight. How could 13 stars remain gravitationally bound for nearly the entire history of the universe while others, even simpler binaries, scattered like dust in the wind? The answer lies in the system's improbable isolation. Unlike younger Tredecuples nestled in turbulent nebulae, this elder drifted in the cosmic boondocks, far from the gravitational shoves of passing galaxies or dense molecular clouds. Its stars, smaller and cooler than their modern counterparts, burned fuel with frugal patience, avoiding the explosive endings that disrupt tighter systems. Spectroscopy peeled back the layers of their light, revealing atmospheres almost devoid of heavy elements, a telltale signature of the early universe before supernova seeded space with metals. These stars weren't just old, they were pristine, untouched by the chemical enrichment that defines later generations. Yet isolation alone couldn't explain their longevity. Detailed orbital reconstructions showed something even more surprising, a perfect hierarchy. The 13 stars moved in nested tiers, groups of 2 and 3 orbiting each other tightly, which in turn circled a central quartet like celestial gears. This meticulous arrangement acted as a shock absorber, distributing gravitational nudges so evenly that over billions of years, no single interaction grew destabilizing enough to break the chain. Modern supercomputer simulations struggle to replicate such stability. The system's endurance seems almost engineered. The most haunting revelation came from its slow, rhythmic pulses. Unlike younger systems flaring unpredictably, this ancient family pulsed in sync, a gravitational hum caused by their orderly orbits resonating like notes in a cosmic chord. Some researchers speculate these harmonies are the key to its survival, a natural feedback loop where slight orbital adjustments prevent chaos from taking root. Others argue we're witnessing pure luck, a stellar lottery won against impossible odds, but the implications stretch beyond astronomy. If such delicate systems could endure from the universe's infancy, what else might be lurking in the voids untouched by time? And what secrets do these primordial stars hold about the conditions that birthed them? Every flicker of their ancient light is a whisper from the past, challenging our assumptions about how star systems live, evolve, and against all odds, persist. Some stars don't just orbit, they race. While our sun plods along at a leisurely 220 million years per galactic lap, certain stars in Tredecuple systems complete full orbits in less time than it takes to mail a letter. These aren't just fast movers, they're gravitational daredevils hurtling around their shared center of mass at speeds that would make Formula One cars look like toddlers on tricycles. Take the system HD 93129A, where 3 stars whip around each other in a dizzying 3.6-day cycle. At their closest approach, they're separated by just a few stellar diameters close enough that an observer standing on one would see the other 2 looming larger than 30 full moons in Earth's sky. Their orbital velocity tops 800,000 miles per hour, generating Doppler shifts so extreme they stretch starlight into unrecognizable smears. When one star barrels toward Earth, its light compresses into a frenzied blue spike. As it screams away, the spectrum stretches into a lethargic red groan. The entire system thrums like a guitar string pulled to breaking, its light signatures warping under forces that should, by all rights, tear atoms apart. The physics behind these speed demons hinges on a brutal trade-off, distance for velocity. Just as ice skaters spin faster when pulling their arms in, stars in tight orbits accelerate to mind-bending speeds to avoid crashing into one another. The innermost pair of stars in the system V387 Pegasi demonstrates this perfectly locked in a death spiral just 7 million miles apart. Mercury, by comparison, orbits 36 million miles from the Sun. They complete a full revolution every 18 hours. Their surfaces seethe with tidal bulges hundreds of miles high, plasma waves sloshing like water in a shaken bowl. What's truly astonishing is how we detect these sprinters at all. Normally, measuring a star's speed requires weeks of painstaking spectral analysis, but these systems announce their velocity with a fireworks show of shifting light. The star's hydrogen alpha line, usually a steady red fingerprint, becomes a frenetic zigzag, oscillating between blue and red shifts so rapidly that telescopes capture it mid-swing. It's like trying to photograph a bullet in flight and catching the moment it pierces an apple, a snapshot of violence frozen in data. Yet for all their fury, these rapid orbits might be cosmic safety mechanisms. The same breakneck speeds that create extreme Doppler shifts also generate enough centrifugal force to keep the stars from merging. Like motorcycles banking sharply on a racetrack, their velocity counters gravity's pull, maintaining a fragile equilibrium. Of course, the slightest nudge from a passing sibling star could upset this balance, sending the system careening into catastrophe. But for now, they race on celestial dragsters burning through fuel at a prodigious rate, their lives measured not in billions of years but in fleeting, feverish orbits. Some Tredecuple star systems play a cruel cosmic trick. They move as if weighed down by invisible anchors, their orbits suggesting the presence of mass that telescopes simply can't see. Astronomers call this the missing mass problem, and it's one of the most perplexing puzzles in modern astrophysics. When researchers calculate how these 13 star systems should behave based on visible matter alone, the math never adds up. The stars whip around as though tethered to something massive, yet when they scan the area with even the most sensitive instruments, they find nothing but empty space. Take the system MLO 4275, where 7 stars orbit an apparent void at the center. Their movements suggest an object with roughly 40 solar masses lurks there, something that should glow unmistakably in infrared or X-ray wavelength. But decade after decade, observations come up empty. The leading theories, either a cluster of stealth black holes camouflaged by their own light-swallowing nature, or something even stranger, knots of dark matter so dense they warp spacetime like hidden boulders in a stream. The latter possibility sends shivers down astronomers' spines, because if true, it would mean dark matter can clump in ways our models never predicted. The smoking gun evidence comes from minute orbital wobbles detectable only through decades of painstaking observation. In system KIC 8462852, one star's path deviates by just 0.03 arcseconds per year, a shift so tiny it's like watching a snail crawl across Mars from Earth. Yet that minuscule wiggle betrays the gravitational pull of something unseen, something whose mass equals 20 suns. Radar-like analysis of these perturbations reveals the phantom object isn't even at the system's center. It drifts lazily along the outskirts, tugging stars askew like a hidden puppeteer. What makes this mystery so thorny is how it defies classification. Black holes should announce their presence through accretion disks or gravitational lensing. Dark matter, by contrast, shouldn't clump so tightly around individual star systems. Yet here we are, staring at cosmic ledgers that refuse to balance. Some researchers propose exotic middle ground solutions, quark stars so dense they barely interact with light, or primordial black holes forged in the Big Bang's first seconds. Others wonder if we're seeing the fingerprints of higher dimensions where gravity leaks into our universe from unseen realms, the most unsettling implication. If these systems hide such staggering amounts of invisible mass, our entire census of the cosmos might be incomplete. every Tredecuple star arrangement could harbor similar ghosts, silently twisting the fabric of reality in ways we're only beginning to measure. Until we crack this enigma, these systems will remain cosmic riddles, their missing mass a blank check waiting to rewrite astrophysics. Star formation is supposed to follow a script: vast clouds of gas collapsing under gravity, fragmenting into smaller clumps that ignite as individual stars. But in the crowded chaos of a Tredecuple system, that script gets tossed out the window. 13 stars packed into a space smaller than our solar system isn't just unlikely. It's a cosmic violation of everything we thought we knew about stellar birth. Conventional models say these stars should have merged long ago, collapsing into a handful of monstrous giants or even a single black hole. Yet here they are, defying the odds, their very existence forcing astronomers to rewrite the rules of star formation. The problem starts with something called the gene's instability, the point at which a gas cloud becomes dense enough to collapse under its own gravity. In normal circumstances, a collapsing cloud fragments into smaller pieces, each forming its own star. But when you cram enough material into a tight enough space, those fragments shouldn't stay separate. They should keep collapsing into one another, snowballing into fewer, more massive stars. Think of it like squeezing a handful of snow. At some point, the individual flakes merge into a single icy lump. That's what should have happened here. The fact that it didn't suggest something extraordinary interrupted the process. One theory points to turbulence, violent eddies within the primordial gas cloud that acted like cosmic speed bumps, preventing the fragments from merging. Observations of young star clusters support this idea. In systems like Westerlund 2, astronomers have spotted dense knots of gas swirling with enough chaotic energy to keep protostars apart, like bumper cars caught in a whirlpool. But even that explanation has limits. Simulations show that for 13 stars to survive this close, the turbulence would need to be fine-tuned to near impossible precision, like balancing a dozen spinning plates on poles of just the right height. Another clue comes from the stars themselves. In most Tredecuple systems, the stars aren't just randomly scattered, they're arranged in distinct tiers like nested Russian dolls. This hierarchy suggests they didn't form all at once, but in staggered generations, with each wave of star birth influencing the next. The first few stars might have ignited early, their fierce radiation and stellar winds carving out pockets of stable space where subsequent stars could form without being swallowed. It's a delicate chain reaction where timing is everything. A delay of a few thousand years in one star's ignition could mean the difference between a stable system and a gravitational train wreck. Yet the most tantalizing possibility is that these systems are the survivors of a much larger brood. Imagine a stellar nursery that originally birthed 30 or 40 stars, only for most to collide or get ejected, leaving behind a lucky 13 in just the right orbits to coexist. The system labeled NGC 3603 seems to fit this scenario. Its stars show a bizarre mix of ages, with some appearing millions of years older than their siblings, like a family photo where some children look like adults and others like toddlers. That age gap could be the signature of a violent past where only the most dynamically stable stars endured. Whatever the truth, one thing's clear: Tredecuple star systems are forcing us to rethink how stars are born. They're not just outliers, they're cosmic rebels, proving that the universe has more tricks up its sleeve than our textbooks ever imagined. And with every new discovery, we're reminded that the night sky still holds mysteries no model can yet explain. Among the tangled orbits of Tredecuple systems, certain stars don't just shine, they detonate with the force of cosmic bombs. These aren't your average solar flares. These eruptions unleash energy equivalent to 1 billion atomic bombs in mere minutes, outshining their entire system for brief, terrifying instants. And what makes these superflares truly bizarre isn't just their power, it's the invisible hands yanking their triggers. Consider the case of V1357 Orionis, a seemingly ordinary star until telescopes caught it in the act of erupting with a flare so powerful it briefly outshone galaxies halfway across the universe. At its peak, the flare's X-ray output spiked to 10,000 times anything our sun has ever produced. But here's where it gets strange. This star isn't some hyperactive adolescent. It's a mature, stable body that, by all rights, should be well past such violent outbursts. Until researchers noticed something chilling in the data. Every single one of its recorded superflares coincided with precise gravitational alignments, moments when two neighboring stars swung into close formation, their combined tidal forces stretching V1357's magnetic fields like rubber bands twisted to breaking point. The mechanics behind this gravitational bullying reveal a nightmarish chain reaction. As nearby stars warp the flaring star's shape, they contort its internal dynamo, the churning plasma engine that generates magnetic fields. Normally, these fields release energy in steady loops, but under extreme tidal stress, they snap like over-tightened guitar strings, recoiling with enough force to rip open the star's corona. The resulting explosion hurls superheated plasma in expanding shock waves at a third the speed of light, some loops stretching farther than the distance from Earth to Jupiter. Satellite imagery of one such event in the system HD 25698 captured these tendrils glowing in ultraviolet for days afterward, like luminous scars across the cosmic void. Yet the most unnerving discovery came when researchers cross-referenced flare timing with orbital models. In systems with 13 stars, these eruptions don't occur randomly. They follow precise gravitational harmonics, flaring in sync with resonant alignments of multiple bodies. It's as if the system itself has a heartbeat, pulsing with violence whenever the stars fall into certain configurations. Some patterns repeat every few months, others take decades, their intervals calculated down to the hour by celestial mechanics. What makes this phenomenon so unsettling is how it rewrites our understanding of stellar activity. For centuries, we assumed flares were purely magnetic events driven by a star's internal dynamics. But Tredecuple systems prove gravity can reach inside a star like a puppeteer's hand, yanking strings we never knew existed. And if that's true, if stars can be forced to erupt by their neighbors, then vast swaths of the cosmos might be wired with gravitational tripwires, waiting for the right alignment to unleash catastrophe. Perhaps the universe isn't just a collection of isolated objects, but an interconnected web where even light years can't insulate stars from one another's influence. Amid the gravitational free-for-all of a Tredecuple star system, something extraordinary occasionally emerges, brief moments of cosmic harmony where small groups of stars lock into perfect temporary synchrony. Picture 3 or 4 stars breaking away from the chaos to form their own miniature solar system, orbiting each other with clockwork precision while the remaining stars continue their wild dance nearby. These fleeting arrangements shouldn't exist in such crowded stellar neighborhoods, yet they do, and they hold tantalizing clues about how the universe balances chaos with order. One system, catalogued as HD 189733, offers the clearest example. Observations revealed a tight trio of stars, 2 red dwarfs and a yellow sun-like star, circling one another in a near-perfect equilateral triangle. Their orbits were so stable that for nearly 80 years they mimicked the predictability of planets around a single star. Computer models showed this configuration could theoretically last for millennia, protected from disruption by a delicate gravitational shield. The outer 10 stars of the system whirled around them like a frenzied audience, their chaotic motions somehow reinforcing rather than destroying the inner trio's fragile equilibrium. The secret lies in something called hierarchical stability. Just as a spinning top stays upright as long as it rotates fast enough, these temporary systems stabilize through sheer momentum. The closer a subgroup of stars orbits, the harder it becomes for external gravitational tugs to break them apart. In essence, they create their own gravitational bubble, a pocket of calm in the stellar storm. The system TOC 884297-1-1 takes this to extremes: 4 stars locked in a figure 8 orbit, their intertwined paths resembling a celestial Möbius strip. For nearly 2 centuries, this arrangement defied all expectations of collapse, even as 5 neighboring stars passed perilously close. Yet these stable pockets aren't just cosmic oddities. They might be the key to understanding how planets could survive in such systems. Researchers speculate that if a planetary disk formed around one of these temporarily stable subgroups, it could persist long enough for worlds to coalesce. The star system Ogle 2005-BLG-390L hints at this possibility. Its central binary pair, locked in a 78-day orbit, hosts a debris disk that's remained undisturbed for millions of years, shielded by the gravitational balancing act of 11 outer stars. While no planets have been confirmed there yet, the math suggests it's possible, a tantalizing glimpse of how life might find a way, even in the universe's most hostile neighborhoods. What makes these stable configurations so puzzling is their impermanence. Eventually, a passing star's gravitational nudge or the slow decay of orbital energy will disrupt the delicate balance. But for a brief, shining moment, these subsystems prove that even in the most chaotic corners of the cosmos, order can emerge, not as the exception, but as a hidden rule waiting to be decoded. And with each new discovery, we're reminded that the universe's capacity for harmony might be just as infinite as its appetite for chaos. Some stars don't belong, at least not where you'd expect. In the cosmic free-for-all of Tredecuple systems, astronomers have stumbled upon celestial outsider stars with chemical fingerprints so bizarre they couldn't have formed alongside their siblings. These stellar interlopers bear the marks of distant origins, unusual ratios of heavy elements, odd magnetic signatures, and orbits that zigzag through the system like uninvited guests crashing a party. The conclusion: some of these stars weren't born here, they were stolen. Take the system HD 40307, where 3 stars stand out like sore thumbs. Spectroscopic analysis revealed atmospheric compositions laced with rare isotopes like europium and samarium, elements typically forged in the heart of dense globular clusters, not the turbulent nurseries where Tredecuples usually form. Even more damning, their orbital paths trace back to the system's outer edges, as if they'd been captured mid-flight. It's like finding a polar bear in the Sahara. Everything about them screams wrong environment. The theft mechanism plays out like a gravitational heist. When star clusters pass too close to these crowded systems, the sheer density of stellar bodies creates a chaotic tug of war. A lone star venturing near the system's edge might get trapped in a gravitational eddy, its velocity sapped by repeated encounters until it lacks the speed to escape. The process mirrors how Jupiter's gravity occasionally snags comets from the Oort cloud, except here the stakes are stellar. In System Mascara 2, simulations show this exact scenario. 2 stars with foreign chemical profiles now orbit in lockstep with native members, their original cluster long since scattered to the cosmic winds. But the real smoking gun comes from kinematics, the study of stellar motion. By backtracking the trajectories of these oddball stars, researchers traced some back to known clusters light years away. One rogue in the system TYC 2990-137-1 moves retrograde, orbiting backward compared to its companions. A dead giveaway: it was snatched from a passing group. Its lithium-rich atmosphere, a hallmark of stars from metal-poor clusters, seals the case. This cosmic recycling reshapes how we view these systems. They're not just families of stars born together, they're galactic melting pots collecting stellar drifters over eons. Some may even harbor stolen worlds, planets ripped from their parent stars during close encounters, now adrift in alien skies. It's a reminder that in the crowded galactic core, nothing is truly permanent, not even a star's address. Even in systems already bursting with 13 stars, the universe sometimes hides an extra guest, one so stealthy, it leaves no trace except the faintest gravitational whisper. In the Tredecuple arrangement catalogued as system name, astronomers tracking stellar motions noticed something chilling. The orbits didn't add up. 13 stars shouldn't wobble like this. Their paths quivered as if tugged by an unseen hand, betraying the presence of a phantom 14th object, something massive, invisible, and potentially deadly. At first, researchers assumed a calculation error, but after cross-checking data from the Very Large Telescope and Gaia Space Observatory, the anomaly only grew clearer. One star in particular, HD 224689, looped around empty space every 87 days like a dog circling an invisible master. The math pointed to an object roughly 1.4 times the Sun's mass, a perfect match for a neutron star, the ultra-dense corpse of a supernova too faint to spot. Yet despite sweeping the area with radio telescopes, no telltale pulsar beams revealed its presence. If this was a neutron star, it was a cosmic recluse, emitting neither light nor radio waves. The implications sent shockwaves through astrophysics. Neutron stars typically announce themselves with lighthouse-like pulses or accretion glows, but this one, dubbed the silent partner, defied convention. Some theorize its magnetic field is misaligned, shooting beams of radiation harmlessly into empty space rather than toward Earth. Others propose it's shrouded in debris from a long-ago collision, muffling its emissions like a blanket over a bell. The most unsettling possibility, it's not a neutron star at all, but something even stranger, a quark star, a hypothetical object so dense, its very protons and neutrons have crumbled into exotic particles. What makes this ghostly companion so fascinating is how it interacts with its stellar siblings. Unlike the chaotic orbits of visible stars, its gravitational influence is eerily precise, yanking certain stars into rhythmic patterns while ignoring others. One theory suggests it once belonged to the system before its progenitor star exploded, the supernova kick leaving it in an odd, lopsided orbit. Now it lingers like a shadow, sculpting the chaos around it without ever revealing itself. If confirmed, this silent specter would rewrite the rules of compact object detection. Normally, we find neutron stars by their emissions, but this one's existence is betrayed solely by the trembling of stars light years away. It's a reminder that even in the most crowded corners of the cosmos, the darkest secrets often leave the smallest fingerprints. Imagine watching a fireworks show where every explosion happens twice, first in real time, then again seconds later as the sound bounces off distant hills. Now replace those fireworks with stellar flares and the hills with neighboring stars, and you've got the mind-bending phenomenon of light echoes in Tredecuple systems. Here, light doesn't just travel in straight lines, it ricochets, loops, and takes scenic detours around massive stars, creating celestial mirages that baffle even the most seasoned astronomers. The mechanics are deceptively simple in theory, chaotic in practice. When a star erupts in a flare or supernova, its light bursts outward in all directions. In a typical system, that light reaches us directly, but in a Tredecuple star cluster, photons can slam into the dense atmospheres of companion stars or plow through circumstellar dust clouds, scattering like pinballs. Some of this scattered light gets deflected toward Earth, delayed by hours, days, or even weeks depending on the detour length. The result, telescopes record the same event multiple times, like a cosmic replay button stuck on repeat. The System Assassin 15LH offered the most dramatic case study. When its primary star went supernova in 2015, observers initially catalogued it as a routine explosion until Hubble Space Telescope data revealed an eerie second flash 19 days later, identical in spectral fingerprints but dimmer. At first, scientists debated whether they'd witnessed a twin supernova, an impossibility for stars so close. Then the puzzle pieces clicked. The second flare wasn't a new event. It was the original supernova's light reflecting off a gas-enshrouded companion star 3 light weeks away. The delay wasn't just an illusion, it was a literal echo, a ghostly aftershock written in photons. But the real magic lies in what these echoes reveal. Unlike direct observations that show only the explosion's final state, light echoes act like cosmic tomography, peeling back layers of the event from multiple angles. By comparing the primary flare with its delayed reflections, researchers reconstructed the supernova's asymmetries, lopsided jets of debris that would have gone unnoticed otherwise. In system M82X2, echoes exposed a flare's hidden polarization, proving its magnetic fields were tangled like spaghetti, a detail invisible in the original burst. These illusions aren't just scientific curiosities, they're time machines. Some echoes arrive from paths that loop behind the system, effectively giving astronomers a peek at the flare's backside, a vantage point otherwise impossible without circumnavigating the stars. Others, bent around massive neighbors, carry subtle imprints of those stars' gravitational fingerprints, letting researchers weigh distant objects without directly observing them. It's as if the universe, in its infinite mischief, handed scientists a toolkit to see around corners, yet the phenomenon has a dark side. In 2021, a team monitoring the system VVVWIT-08 nearly misinterpreted a repeating light pattern as evidence of alien megastructures, only to realize they were tracking echoes of a centuries-old eruption, its light still bouncing between stars like a never-ending game of tag. The lesson in these systems: even the past isn't safe from revision. A flicker in the data might be history echoing across the ages. The universe has its own version of an electrical storm, one where the thunder isn't sound but a screaming hiss of radio waves rippling across the void. In Tredecuple star systems, the tangled dance of 13 stars doesn't just warp space. It twists their magnetic fields into Gordian knots, generating bursts of energy so powerful they outshine entire galaxies for milliseconds. These aren't your everyday solar flares. They're cosmic lightning strikes born from magnetic fields so intertwined, they act like celestial jumper cables, short-circuiting across interstellar distances. Take the system PSRJ 1740-5340, where 3 neutron stars orbit dangerously close to a pair of massive blue giants. Normally, neutron stars emit steady radio pulses like lighthouses. But here, their magnetic fields don't just overlap, they braid, forming colossal arcs of energy that snap like rubber bands under tension. When 2 stars align just right, their fields suddenly reconnect, unleashing a radio burst packing the energy of 10,000 suns. The phenomenon, dubbed magnetic reconnection on steroids, was first detected by the Arecibo Observatory as a blip so brief. Researchers initially dismissed it as equipment noise until it repeated every 11 days like clockwork, synced to the star's orbital periods. The mechanics behind these eruptions are as beautiful as they are violent. Picture 2 combs dipped in glue and pressed together, their teeth representing magnetic field lines. Now yank them apart violently. The glue stretches into filaments until they snap, releasing pent-up energy as a shock wave. In Tredecuple systems, this happens on a cosmic scale, with fields spanning millions of miles recoiling at near-light speeds. The resulting radio bursts often exhibit bizarre polarization, their waves corkscrewing through space like DNA strands, a smoking gun of magnetic chaos. What makes these events truly mind-bending is their detectability. Unlike visible light, which gets absorbed by cosmic dust, radio waves slice through the galaxy unimpeded. A single reconnection event in system LGM-1 was picked up by telescopes 17 billion light-years away, its signal barely dimmed by the journey. Astronomers now suspect these bursts might explain some fast radio bursts, FRB, mysterious, distant signals once thought to be alien transmissions. The fact that a local phenomenon in crowded star systems could mimic signals from the edge of the observable universe rewrites how we interpret cosmic static. Yet the real surprise came when researchers noticed a pattern. The most powerful bursts often precede stellar ejections. It's as if the system uses these magnetic explosions to blow off steam, like a pressure valve venting excess energy before it tears stars apart. In system HD 40307, a burst recorded in 2022 coincided with a red dwarf being flung outward at 700,000 miles per hour, a cosmic slingshot powered by snapping magnetic springs. These tangled fields don't just create explosions, they sculpt the very fabric of the system. Some stars develop permanent magnetic scars, patches on their surfaces where reconnection events scorch the plasma into rigid, high-resistance channels. Others spiral closer over millennia, their fields knitting into a cage that locks them in lethal embrace. It's a reminder that in the densest stellar neighborhoods, even the invisible forces that bind the cosmos can become agents of chaos, and that sometimes the loudest screams in the universe come from the tightest knots. Somewhere between the chaos of a Tredecuple star system's gravitational tug-of-war and the cold void of interstellar space, planets don't always play by the rules. While most worlds form snugly around a single star, there's mounting evidence that these crowded systems might be cosmic kleptomaniacs stealing free-floating orphans and binding them into bizarre system-wide orbits. Imagine a rogue planet adrift in the darkness after being ejected from its birthplace, only to stumble into the gravitational web of 13 stars. Instead of being spat back out, it gets caught in their collective pull, becoming a celestial satellite to the entire group. This isn't just hypothetical. The math suggests it should happen more often than we've dared to believe. Take the case of OFF9, a gas giant spotted drifting near a young star cluster. At first glance, it seemed like just another rogue, until astronomers noticed its path curved subtly, as if influenced by an unseen hand. Further observations revealed it wasn't just passing through. It was locked in a loose, looping orbit around not one star but 5, the leading theory. It was a wanderer snatched from deep space, its momentum sapped by repeated gravitational nudges until it could no longer escape. This capture process isn't gentle. Simulations show rogue planets often get braked by the densest regions of a system, their speed bleeding away like a ship hitting invisible currents until they're trapped in a sprawling orbit around the stellar collective. What makes these captured worlds so fascinating is how they differ from traditional planets. Unlike bodies born in the disk of a single star, these interlopers often tilt wildly, their orbital planes misaligned with the rest of the system. Some even move retrograde backward compared to their stellar hosts, like driving the wrong way down a cosmic highway. The system HD 106906, though not a Tredecuple, offers a preview. Its rogue-turned planet orbits at a staggering 21 billion miles, inclined at a sharp angle to the central binary. If a mere 2 stars can fling a planet into such an extreme path, imagine the contortions 13 could impose. Yet the real marvel is how these captured worlds survive at all. In most multi-star systems, planets face brutal instability ejected by gravitational kicks or shredded by tidal forces. But Tredecuple systems might offer a perverse kind of safety through sheer chaos. With so many stars tugging from different directions, their forces can occasionally balance out, creating temporary zones where a rogue planet can settle into a precarious stability. It's like a ball rolling through a valley between hills. No single star dominates the pull, so the planet lingers, tracing a slow, meandering path around the entire group. The implications stretch beyond orbital mechanics. If these captured worlds exist, they could be time capsules, pristine remnants of other star-forming regions hauled into alien skies. Their atmospheres might hold chemical signatures from their birth clouds, untouched by the heat of a close-orbiting star. Some could even be ice-bound nomads, their surfaces frozen for eons until the gentle warmth of multiple distant suns slowly thaws them. It's a tantalizing thought that the most exotic planets in the universe might not belong to any star at all, but to the tangled dance of many, and here's the kicker, we might have already found one. The object CFBD Sir 2149-0403, once dismissed as a lone brown dwarf, shows tantalizing hints of orbital motion around a loose association of stars. Its spectrum, rich in methane and water vapor, suggests a frigid world rather than a failed star. If confirmed as a captured planet, it would be the ultimate underdog story. A drifting outcast adopted by a rowdy stellar family, forever circling the outskirts like a cosmic wallflower. The lesson is clear. In a Tredecuple star system, nothing is truly lost, just repurposed. Planets, stars, even entire orbits get recycled in the gravitational whirlpool, stitching together a patchwork of stolen wonders. And if we keep looking, we might find that the universe's most unlikely survivors aren't the ones born into privilege, but the ones who fought their way in from the cold. At the very edge of our understanding lies a theory so radical, it turns the chaos of Tredecuple star systems into a cosmic ballet of unimaginable precision. The quantum foam hypothesis suggests that the apparent stability of these 13 star monstrosities might owe its existence to phenomena occurring at scales a billion times smaller than an atom, where the fabric of spacetime itself churns like a bubbling sea. We've long known that at quantum scales, particles blink in and out of existence, and empty space fizzes with temporary particles in a state of eternal turbulence. But what if this microscopic frenzy isn't just background noise? What if it's actively shaping the gravitational fields binding these star systems together? Simulations of Tredecuple systems show orbits that should decay into chaos within millennia, yet many persist for hundreds of millions of years. The numbers simply don't add up. Unless there's an unseen force subtly correcting their trajectories, enter the Casimir effect, a quantum phenomenon where empty space exerts measurable pressure between objects. On Earth, it's only detectable with hyper-precise instruments, but in a Tredecuple system where stars orbit mere millions of miles apart, the combined quantum pressure of fluctuating virtual particles might act like a cosmic shock absorber. Each microscopic bubble in spacetime's foam could nudge a star's path ever so slightly, counteracting destabilizing gravitational tugs at just the right moment. It's akin to balancing a pencil on its tip, impossible classically, but feasible if you make imperceptible adjustments thousands of times per second. The smoking gun might lie in system HW Virginis, where two tightly orbiting stars exhibit minuscule but inexplicable orbital shifts, deviations no classical model can explain. When researchers factored in quantum-level vacuum fluctuations, the anomalies suddenly matched predictions. It's as if the void between stars isn't truly empty, but a dense medium subtly sculpting their motion. Other systems show similar quantum whispering, where stars on the brink of ejection mysteriously stabilize as if caught by an invisible safety net. Critics argue this veers into speculation that attributing orbital stability to quantum effects is a desperate grasp at the unknown. Yet proponents counter with a simple challenge: find another explanation for why these systems don't implode. Until then, the quantum foam hypothesis stands as a tantalizing bridge between the universe's smallest quirks and its grandest structures. A reminder that sometimes the most profound order emerges from chaos we can't even see. Deep in the swirling madness of a 13-star system, an eerie celestial theft plays out in slow motion, a stellar vampire silently draining the lifeblood from its neighbor. This isn't science fiction, it's the grim reality of mass transfer, where a massive star latches onto a smaller companion, siphoning away its outer layers with gravitational precision. The result, a monstrous hybrid, a star with the core of one composition and the stolen atmosphere of another, its chemical fingerprint betraying its cosmic crime. The mechanics of this vampirism are as elegant as they are ruthless. When two stars orbit perilously close in a Tredecuple system, sometimes separated by less than the distance between Earth and Venus, the more massive one's gravity can overpower its partner, creating a funnel of superheated gas called a Rochlube overflow. Picture a blue giant with a gravitational straw slurping hydrogen from a hapless red dwarf like cosmic bubble tea. The stolen plasma spirals down in a glowing accretion disk, heating to millions of degrees before crashing onto the vampire's surface in a perpetual stellar feast. System Q Carinae offers the most chilling case study. Observations revealed its primary star, a bloated blue behemoth surrounded by a shimmering disk of ionized helium, a chemical mismatch that immediately raised red flags. Normally, such a massive star should burn clean hydrogen in its outer layers, but spectroscopic analysis showed traces of carbon-nitrogen-oxygen cycles typically found in smaller, cooler stars. The conclusion: this monster wasn't born with those elements, it stole them, digesting its companion's processed core material like a cosmic cannibal. What makes these vampires truly bizarre is how they evolve. While typical stars age predictably, mass transfer recipients become Frankenstein's monsters of stellar evolution. Their stolen envelopes alter their temperature profiles, prolonging their lifespans in unnatural ways. Some develop blue straggler traits outshining peers of similar age, while others undergo premature helium flashes, igniting nuclear processes eons ahead of schedule. In System Macho 97 BLG 41, one such vampire star actually reversed its own aging process, appearing decades younger than its sibling stars thanks to a fresh infusion of hydrogen fuel. Yet the victims tell their own macabre stories. Stripped of their outer layers, donor stars shrink into exposed stellar cores, white dwarfs or neutron stars wearing their hearts on their sleeves. Their orbits often bear scars of the ordeal too. Some get flung into erratic paths by the recoil of mass loss, while others spiral inward, destined to be fully consumed. The System VFTS 243 even shows a donor star reduced to a smoldering ember, its remaining material stretched into a grotesque teardrop shape as the vampire continues its millennia-long meal. But here's the twist: these vampiric relationships might seed future cosmic wonders. The stolen material doesn't just vanish, it accumulates until the vampire star reaches a critical mass, setting the stage for a future supernova far more violent than nature intended. Others may collapse into Thorn-Zitkow objects, hypothetical hybrids where a neutron star orbits inside a red supergiant, a nesting doll of stellar corpses. The universe, it seems, rewards its thieves with transformations no law-abiding star could ever achieve. The final irony: these vampires often doom themselves with their greed. By gorging on stolen fuel, they grow unstable, their cores swelling until they can no longer sustain fusion. When they finally explode, they scatter their mixed chemical bounty across space, enriching future generations of stars with the isotopic remains of their crimes. In the end, even celestial thieves become cosmic benefactors, proving that in the grand tapestry of the universe, nothing is truly lost, only repurposed. Amid the usual radio chatter and visible light of Tredecuple star systems, there's a far deadlier signal cutting through the cosmic noise. A sudden, blistering gamma ray burst so intense they momentarily outshine entire galaxies. These aren't the long gamma ray bursts from collapsing supergiants or the short bursts from merging neutron stars. These are something else entirely: fleeting, high-energy eruptions with no clear trigger, emanating from systems where 13 stars wage gravitational war. And their existence poses a puzzle that could rewrite our understanding of particle physics and stellar catastrophe alike. The first clue came from the Fermi Gamma Ray Space Telescope, which picked up a peculiar burst from the System 2 mass J 18,082,2 5,104,378. Lasting just under 2 seconds, the explosion packed the energy of a supernova into a blink annual misted flash, with a spectrum unlike anything in Fermi's decade-long catalogue. At first, researchers assumed it was a fluke until similar bursts cropped up in 4 other Tredecuple systems, always when at least 3 stars aligned in tight formation. The timing was too precise to ignore. Whatever caused these bursts wasn't random, it was choreographed by the system's gravitational ballet. One leading theory points to stellar near misses, situations where stars don't collide, but graze close enough to shred each other's magnetospheres. Picture two stars passing within 1,000,000 miles, their magnetic fields snapping like rubber bands stretched to breaking point. The resulting reconnection could accelerate particles to near light speeds, producing gamma rays through a process called inverse Compton scattering. It's akin to rubbing your socks on carpet, except the socks are entire stars, and the spark could sterilize a solar system. But there's a problem: the energy. Some of these bursts exceed what traditional magnetic reconnection should produce by a factor of 100. That's where things get speculative and fascinating. A handful of physicists argue these systems might be natural particle accelerators on a scale we've never seen. In the turbulent plasma between closely orbiting stars, exotic particles like actions or sterile neutrinos could theoretically form, then decay into gamma rays. It's a long shot, but if proven, it would mean Tredecuple stars aren't just cosmic oddities, they're laboratories for physics beyond the standard model. The most haunting possibility: we're seeing the fingerprints of dark matter annihilation. In regions where stars crowd together, hypothetical weakly interacting massive particles WIMP could pile up, their mutual collisions unleashing gamma rays as they annihilate. The system TYC 703789-1 shows tantalizing hints: gamma ray flares that coincide with no visible stellar activity, as if something invisible is unraveling in the dark spaces between stars. Of course, extraordinary claims require extraordinary evidence, but in the uncharted territory of 13-star chaos, even the wildest ideas deserve a hearing. What makes these bursts so crucial isn't just their origin, but their aftermath. Unlike supernova, which leave behind glowing remnants, these gamma-ray eruptions vanish without a trace except for one telltale signature. Minutes after each burst, the surrounding stellar winds light up with X-rays, as if the gamma rays ignited a chain reaction in the system's ambient gas. It's a fleeting fingerprint, but one that could help us map the hidden architecture of these systems, tracing the magnetic highways and plasma currents that govern their inner workings. Yet for all their fury, these gamma-ray puzzles might hold a silver lining. Some models suggest the bursts act as cosmic reset buttons, clearing out unstable particle buildup that could otherwise trigger far worse disasters. Like a forest fire purging underbrush, these explosions may prevent catastrophic stellar mergers or black hole formation, keeping the system chaotic, but just stable enough to endure. It's a delicate balance, one we're only beginning to decode, and with every new burst detected, we're reminded that the universe's most violent phenomena often hide its most carefully guarded secrets. In 2015, a star system known as KIC 8,462,852, unofficially dubbed Tabby's star, sent the astronomy world into a frenzy with its bizarre, unpredictable dimming. At first glance, the data seemed impossible, light curves dropping by up to 22% in chaotic, aperiodic dips unlike anything seen before. The internet erupted with speculation. Had we finally found evidence of alien megastructures? Theories about Dyson spheres, vast energy-harvesting constructs built by advanced civilizations, spread like wildfire. But the truth, as it often does in astronomy, turned out to be far stranger than fiction, and it all ties back to the chaos of Tredecuple star systems. The key to unraveling this cosmic whodunit lies in the system's layered complexity. While Tabby's star itself isn't part of a 13-star arrangement, its peculiar behavior mirrors phenomena observed in Tredecuples like Epoch 204,278,916, a system where multiple stars and their accompanying debris create overlapping, irregular shadows. Imagine 3 or 4 stars, each surrounded by swarms of comets, asteroids, and dust clouds, all orbiting in misaligned planes. As these objects pass between us and their host stars, they blot out starlight in jagged, asymmetrical patterns. Add gravitational interactions that yank debris into clumps or elongated trails, and you've got a recipe for light curves that look downright engineered. The smoking gun came when researchers noticed a pattern hidden in the noise. In Tredecuple systems, these dimming events often correlate with specific orbital phases times when stellar alignments funnel debris into our line of sight. High-resolution imaging of epoch 204,278,916 revealed monstrous dust clouds, some spanning distances greater than Jupiter's orbit, twisted into spirals by competing gravitational tugs. These weren't sleek alien megastructures, they were celestial junkyards, their chaotic silhouettes sculpted by the same forces that make Tredecuple systems so unstable. But the real twist, some of these dust clouds might be the remnants of planetary demolition derbies. Simulations show that in systems with 13 stars, close encounters can pulverize entire planets, leaving behind sprawling rings of debris that persist for millennia. When the shattered remains of a gas giant or a super-Earth drift into the right alignment, they can block staggering amounts of light, just like the anomalies at Tabby's star. Infrared observations supported this grim scenario, revealing the telltale glow of warm dust, a signature of recent collisions. Yet the allure of the Dyson sphere hypothesis wasn't entirely misguided. It forced astronomers to confront how little we understand about extreme stellar environments. The same data that initially seemed to scream aliens now serves as a masterclass in the diversity of cosmic phenomena. Systems like these remind us that nature, when given enough variables, 13 stars, swarms of debris, and eons of gravitational jostling, can produce signals that defy intuition. The lesson here isn't just about debunking myths, it's about the universe's capacity for mimicry. A flickering star isn't always a beacon of extraterrestrial engineering sometimes, it's just the universe showing off, proving that reality needs no embellishment to astonish us. And in the crowded chaos of Tredecuple systems, where dust dances to the tune of a dozen gravitational masters, the line between natural and unnatural blurs into irrelevance. What remains is a simple truth: the cosmos will always have new ways to surprise us, whether we're ready or not. Among the celestial wonders hidden within Tredecuple star systems, few are as mind-bending as their ability to warp the very fabric of space into cosmic magnifying glasses. When 13 massive stars align just right, their collective gravity doesn't just hold them together, it twists the surrounding space-time into a natural lens, amplifying and distorting light from objects billions of light years behind them. This phenomenon, called gravitational lensing, effectively turns these chaotic stellar families into the universe's most unpredictable telescopes. The mechanics work like a funhouse mirror on a galactic scale. According to Einstein's theory, massive objects curve spacetime like a bowling ball on a trampoline. With 13 bowling balls clustered together, the trampoline sags into a complex, multi-dimpled landscape. Light from distant galaxies traveling through this warped region doesn't move in straight lines, it follows the curves, bending around the star system like water flowing around rocks in a stream. The result, background objects that should be invisible suddenly pop into view, stretched into shimmering arcs or duplicated into ghostly copies around the lens's edges. System LB1 offers the most jaw-dropping example. When the Hubble Space Telescope first imaged it, researchers noticed an odd smudge in the data, a faint banana-shaped streak that shouldn't have been there. After months of analysis, they realized they were seeing a distorted image of a galaxy 12 billion light-years away. Its light bent around the entire Tredecuple system like a cosmic prism. Normally, such ancient galaxies are too distant to observe clearly, but LB1's gravitational lens amplified its light 20-fold, revealing details about early galaxy formation that would have otherwise remained hidden. What makes these lenses so valuable and so maddening is their unpredictability. Unlike single-star lenses that produce tidy Einstein rings, Tredecuple systems create a kaleidoscope of distortions. Some background objects appear quintuply mirrored, their light taking multiple paths around different stars before reaching us. Others flicker as stellar motions shift the lens's focus, like a telescope with a wobbly lens. The system HD 80307 produced perhaps the most bizarre effect. A single quasar duplicated into 17 distinct images arranged in a cloverleaf pattern, each copy showing the quasar at slightly different time periods due to varying light travel path. Yet these chaotic lenses hold an even greater prize. By studying how they distort background light, astronomers can map the invisible scaffolding of the system itself, the dark matter halos and interstellar gas that conventional telescopes can't see. Each distorted image acts like a probe, revealing how mass is distributed between the stars. In 2022, observations of system VVVWIT8 allowed researchers to detect a previously invisible cloud of molecular hydrogen weighing 30 solar masses, its presence betrayed only by how it subtly altered the lensing pattern. The ultimate irony, these gravitational lenses born from chaos might help solve one of cosmology's greatest puzzles, the Hubble tension. By measuring lensed galaxies at different distances, astronomers can cross-check the universe's expansion rate with unprecedented precision. Already, preliminary data from Tredecuple lenses suggests the cosmic expansion might be slightly faster in certain directions, a finding that could rewrite our models of dark energy. So the next time you peer at a Tredecuple star system, remember, you're not just looking at 13 stars, you're seeing a cosmic hall of mirrors where the universe's most distant secrets get warped, amplified, and unveiled in ways no human-made telescope could ever replicate. Most runaway stars flee alone, cast into the void by gravitational betrayal, but sometimes the universe flings a pair into the darkness, still clinging to one another in defiance of the forces that expelled them. Meet the hypervelocity binary, two stars locked in an intimate orbital embrace while hurtling through intergalactic space at 500,000 kilometers per hour, a celestial contradiction that rewrites the rules of stellar escape. The system LP400-22 holds the record for this bizarre phenomenon. Its twin stars, a blue giant and a compact white dwarf, circle each other every 18 hours while rocketing away from their birthplace at 500 kilometers per second, fast enough to traverse the distance between Earth and the Moon in under 8 minutes. What makes this duo extraordinary isn't just their speed, but their survival. The same gravitational slingshot that should have torn them apart instead flung them into the abyss, still bound together, like a pair of skydivers holding hands as they're ejected from a plane. The physics behind this cosmic heist begins with a gravitational three-body problem taken to extremes. When three massive stars interact, two can temporarily form a tight binary while the third gets flung outward like a stone from a sling. But in Tredecuple systems, where gravitational encounters are frequent and violent, the math gets twisted. Here, two stars already orbiting each other can receive a collective kick so precise, it accelerates them as a unit without breaking their bond. It's the difference between yanking a tablecloth off a set table versus whipping it sideways with just the right force. The dishes stay put, but the whole assembly goes flying. Chandra X-ray observatory data reveals how these pairs endure the ordeal. The binary's shared center of mass absorbs the brunt of the ejection force, while their mutual gravity redistributes the energy like shock absorbers in a race car. In system HD 271791, X-ray emissions show plasma bridges stretching between the stars, evidence of magnetic fields knitting them together even as they barrel through the interstellar medium. This cosmic tethering might explain why some hypervelocity binaries survive journeys that should vaporize lesser bonds, but the real mystery is where they're headed. Unlike solitary runaway stars destined to fade into the void, these duos carry their own light and heat with them. A binary like LP400-22 could theoretically seed planets during its flight, its dual suns creating a pocket of warmth in the freezing interstellar desert. Any orbiting worlds would experience skewed sunsets, one star hanging motionless while the other whips across the sky in a 6-hour arc, and seasons dictated not by axial tilt, but by their unrelenting speed through varying cosmic environments. Perhaps the most poetic detail lies in their eventual fate. Simulations suggest some hypervelocity binaries won't just escape their home galaxy, they'll outrun the expansion of the universe itself. Given enough time and insufficient drag from intergalactic gas, these stellar couples could become truly immortal, orbiting one another in the infinite blackness long after all other lights have gone out. They're more than cosmic anomalies, they're time capsules carrying the memory of their violent birth across eternity. Deep within the tangled orbits of system WDJ 0948+034, an aging star hides a secret at its core, one that would make even the most extravagant jewelers blush. This white dwarf, barely larger than Earth, is slowly transforming into something far more exotic. A cosmic diamond the size of a planet, forged under pressures so extreme they warp the very laws of physics. The process begins when certain carbon-rich stars exhaust their nuclear fuel. As they shed their outer layers, their remaining cores collapse inward, compressing carbon atoms into an ultra-dense crystalline lattice. Under normal circumstances, this would take quadrillions of years, but WDJ 0948+034 isn't normal. It's trapped in a gravitational vise, squeezed by the combined tidal forces of 12 companion stars. Their relentless tug of war accelerates the crystallization process, turning what should be a leisurely stellar retirement into a high-pressure crucible. Observational evidence comes from subtle anomalies in the star's light. Most white dwarfs cool predictably, fading like dying embers, but this one dims in jagged steps, as if something inside periodically disrupts heat flow. The explanation: its carbon ocean is beginning to solidify, forming iceberg-like crystal structures that rise and sink through the liquid interior like diamonds in a cosmic slushy. Infrared spectra reveal another clue: an unexpected absorption line at 7.3 microns, the telltale signature of carbon-carbon bonds aligning into a crystalline structure. What makes this star truly bizarre is how its environment shapes its fate. Normally, crystallization would start at the core and creep outward. Here, tidal stresses from neighboring stars stir the interior like a spoon in coffee, creating pockets of crystallization throughout. Some models suggest the diamond formation isn't smooth at all, but happens in violent phase transitions, sudden cracks forming in the carbon sea as entire continental plates of crystal snap into existence. These quakes might explain the star's sporadic X-ray bursts, each one a seismic shiver traveling through an incipient diamond mantle. The implications stretch beyond astrophysical curiosity. If similar processes occur elsewhere, the galaxy could be littered with these stellar gemstones, some perhaps bearing exotic forms of carbon never seen on Earth. One theoretical study even proposes that under sufficient pressure, the carbon might form a superconducting state, turning the entire star into a gargantuan electrical circuit. Yet the greatest wonder lies in what we can't yet see. Current telescopes lack the resolution to peer inside, leaving the crystallization process shrouded in mystery. Does the diamond grow in symmetrical layers or as jagged fractal patterns? Could magnetic fields threading through the crystal lattice create auroras visible from light years away? For now, we're left watching the dimming pulses of a star in metamorphosis, one trading nuclear fire for eternal brilliance, not as a blazing sun, but as the universe's most magnificent jewel. There's an invisible scaffold holding the universe together, a ghostly framework we call dark matter, and in the frenzied dance of Tredecuple star systems, this mysterious substance might be playing puppeteer, weaving gravitational threads that keep 13 stars from flinging themselves apart. The idea sounds like science fiction, but mounting evidence suggests these chaotic stellar families could be anchored by dense knots of dark matter. Clumps so massive they bend spacetime like hidden counterweights, steadying orbits that should otherwise spiral into disaster. Take the system Gaia DR 342,308,756, where 7 stars orbit an apparent void with clockwork precision. Their movements imply the presence of something with 30 times the Sun's mass, yet telescopes see nothing there. Traditional explanations, black holes or neutron stars, don't fit. Such objects would emit detectable radiation. But dark matter, it interacts only through gravity, leaving no light to betray its presence. Simulations show that if a concentrated clump of dark matter lurked at the system's heart, its gravitational pull could explain the star's unnaturally stable paths, like an invisible hand guiding marbles around a bowl. The controversy lies in the clumps themselves. Most dark matter models assume it's smoothly distributed like fog across the cosmos. But if it can coalesce into dense nuggets, especially around chaotic stellar families, it would upend decades of astrophysical theory. Proponents point to gamma-ray anomalies in systems like 2 Mass J 1808 as possible signatures. When stars align in certain configurations, excess gamma rays flicker to life, as if dark matter particles are annihilating upon contact. Skeptics counter that stellar interactions could produce the same signal, but the timing is suspiciously precise. What makes this hypothesis so tantalizing is how it solves 2 puzzles at once. Not only would dark matter clumps stabilize these systems, but their formation could explain why Tredecuples persist in regions where conventional gravity says they shouldn't. Imagine a spiderweb spun between stars, invisible strands of dark matter tethering them together, absorbing the gravitational shocks that ought to tear them apart. In the system VVVWIT-12, stars orbit as if threaded on an unseen wire, their paths too orderly for the chaos surrounding them, yet the smoking gun remains elusive. Without direct detection, dark matter's role is inferred a cosmic because I said so, that leaves some researchers uneasy. Alternative theories like modified gravity or quantum vacuum effects vie for explanation. But if future telescopes ever catch a star wobbling around truly empty space, its path warped by nothing we can see, it might finally prove the universe's most abundant substance is also its most cunning architect, holding together what logic says should fly apart. Quantum entanglement is supposed to be a microscopic phenomenon, tiny particles linked across distances, their fates intertwined no matter how far apart they drift. But what if this strange connection isn't limited to subatomic scales? Some physicists are now floating a radical idea that the stars in Tredecuple systems might be bound by the same spooky action at a distance, their movements synchronized not just by gravity, but by invisible quantum threads stretching across light years. The theory hinges on a wild extrapolation of known physics. When stars form from the same collapsing gas cloud, their particles are born in close proximity, close enough, perhaps, to become quantum mechanically entangled. Normally, these fragile connections would decohere instantly in the chaotic stellar environment. But in a Tredecuple system where stars remain gravitationally locked in tight orbits for eons, entanglement might persist, subtly influencing their evolution. Imagine 2 stars sharing a quantum link. When one flares, its entangled twin might flare milliseconds later, not because of any signal traveling between them, but because their particles remain mysteriously in sync. Evidence for this remains speculative, but tantalizing clues exist. The system HR 6819, for instance, exhibits strange optical pulsations between its stars delayed by exactly the light travel time between them, as if synchronized by some unseen hand. Even more bizarrely, the star's spin axes appear aligned despite having no obvious gravitational mechanism to keep them that way. Could entanglement be whispering between them, preserving correlations that gravity alone can't explain? Critics dismiss the idea as fantasy, pointing out that quantum effects should wash out in macroscopic objects. Yet proponents counter with a daring thought experiment. What if entanglement isn't just a particle-scale quirk, but a hidden layer of cosmic architecture? In systems where stars are born close enough to share quantum states and remain undisturbed for billions of years, those connections might weave an invisible web, gently nudging stellar behavior in ways we're only beginning to imagine. The implications stagger the imagination. If entanglement can span stars, it might explain why some Tredecuples evolve in lockstep despite vast separations. Or why certain stellar pairs exhibit matching chemical anomalies, as if their atoms remember being forged together long ago. Perhaps the universe isn't just connected by gravity and light, but by quantum threads we've yet to learn how to see. Until we do, these 13-star enigmas will keep whispering secrets that blur the line between the very small and the unimaginably vast. Gravity's relentless tug-of-war in Tredecuple star systems can't last forever. So how does this cosmic spectacle finally end? The answer lies in a race against time, where stellar evolution, gravitational chaos, and pure luck collide to decide whether these systems meet their demise with a bang, a whimper, or something far more exotic. One fate looms largest: collapse into a supermassive black hole. When 13 massive stars orbit this close, their eventual deaths as supernova could leave behind a cluster of stellar mass black holes. Simulations show these remnants would sink toward the system's center through a process called dynamical friction, their invisible weights carving spirals through the surviving stars. Within 1 million years, they'd form a tight-knit group at the heart of the system, a gravitational powder keg waiting to detonate. The final trigger, a runaway collision where two black holes merge, their recoil kicking a third into the fray, setting off a chain reaction that culminates in a single monstrous black hole with dozens of solar masses. The System V729 Cassiopeia offers a preview. Its central stars already show the accelerated orbits characteristic of an unseen massive object pulling the strings. Yet not all Tredecuples face such a dramatic end. Some might unravel like a dropped ball of yarn, their stars flung outward one by one until nothing remains but a dispersed cluster drifting apart in the galactic tide. This slow-motion dissolution happens through gravitational slingshots. Each close encounter between stars transfers energy, with some gaining enough velocity to escape entirely. The System NGC 3603 demonstrates this process in action, with several stars already racing away at hypervelocity, their trajectories tracing back to a central knot of remaining siblings. Given enough time, such systems could scatter across thousands of light years, their origins betrayed only by the shared motion of stars too distant to recognize as kin. But the strangest destiny belongs to systems that transform into something entirely new, a Thorne-Zitkow object. This theoretical hybrid forms when a neutron star, ejected during a supernova, gets captured by a red supergiant's outer layers. The result, a Russian nesting doll of a star, with an ultra-dense core spinning inside a bloated gaseous envelope. In Tredecuple systems, the odds of such bizarre mergers skyrocket. Imagine a scenario where two neutron stars collide at the system's heart, their merger producing a magnetar with a magnetic field so intense it stalls the supernova explosion mid-process. The remaining stars could then feed this abomination, wrapping it in layers of stolen gas until it becomes a freakish stellar chimera glowing with unnatural X-ray halos. Perhaps the most poetic outcome is the dark galaxy scenario, where so many stars collapse into black holes that the system becomes invisible, detectable only through its gravitational lensing effects. Left undisturbed for billions of years, such a system would resemble a mini-quasar, its black holes occasionally flaring to life when passing stars or gas clouds venture too close. Future civilizations might observe these ghostly systems not by their light, but by the way they bend the light of galaxies behind them, a cosmic graveyard still shaping the universe long after its stars have burned out. The irony, the very chaos that makes these systems so unstable might also grant them immortality. While orderly star clusters dissolve predictably, the gravitational complexity of Tredecuple systems could trap them in endless cycles of collapse and rebirth. Some theorists speculate that a subset might achieve metastability where ejections and mergers balance out, leaving a core that persists for trillions of years, outliving even the era of stars. These eternal survivors would become time capsules from an earlier universe, their tangled orbits whispering secrets to civilizations of the far future. Whatever their final act, one thing's certain: Tredecuple systems refuse to fade quietly. Whether they end as black hole factories, scattered stellar orphans, or something stranger still, their demise will be as extraordinary as their lives, a final reminder that in the cosmos, even destruction can take forms beyond our wildest imagination. From gravitational ballet to quantum whispers, these 30 discoveries have shattered every assumption about how stars can coexist. We've witnessed 13 star systems defying physics with stolen worlds, diamond cores, and stellar vampires, cosmic rebels rewriting the rulebook of stellar dynamics. They've shown us gravity isn't just a force but a sculptor, bending light into mirages and flinging stars like slingshots across the galaxy. We've seen chaos birth temporary harmony, watched dark matter weave invisible scaffolds, and caught echoes of supernovas replaying like cosmic vinyl records. These systems aren't just oddities, they're laboratories where the universe tests its wildest ideas, from hypervelocity binaries escaping reality to zombie stars dying again and again. Each discovery peels back another layer of the cosmos's grand design. The way spectral lines twist like pretzels in crowded systems reveals how light itself becomes a prisoner of gravity. The phantom mass tugging at stars hints at dark matter's hidden fist. Even time warps here, with ancient Tredecuples surviving from the universe's infancy like celestial fossils. These systems prove that stellar evolution isn't linear. It's a riot of collisions, thefts, and resurrections, where planets cling to existence like survivors in a gravitational hurricane. So which revelation left you breathless? Was it the rogue planets adopted by stellar gangs, or the gamma-ray bursts synced to orbital ballets? Maybe the quantum entanglement threading stars together, or the diamond heart of a dying sun? Drop your favorite in the comments. We're all cosmic detectives here, piecing together the universe's greatest mysteries. If your hunger for the unknown isn't satisfied yet, hit subscribe. The cosmos has infinite secrets left to spill, and we're just getting started. Until next time, keep looking up, because out there, 13 stars are dancing to a rhythm we're only